last thing of the year that we need to learn about. We're going to talk about heat and wave that are non-homogeneous. So like I already said, this is going to be a little bit more tedious than what you've already done. So before we start the new stuff, I want to look at what we've done so far. So far we've looked at a problem that looks like this. So my first question to us is this heat or wave? This is heat. What do these two conditions tell us? The ends are held at 0. This is also what makes the equation homogeneous, those two zeros. So the ends are held at 0. And what is this? The initial temperature throughout. So that was before what we're doing. Today, like I already said, we're looking at non-homogeneous boundary value problems. Okay, there are two different meanings for non-homogeneous, or two different possibilities. Either the partial differential equation or the boundaries are non-homogeneous. So it could be the partial differential equation, could be the boundaries, could be both. There are two different kinds of non-homogeneous boundary value equations for wave and heat. We have time independent and then we have time dependent. Each one has its own solving strategy. So today we're going to discuss time independent. Tomorrow we'll discuss time dependent. Here's what a time independent partial differential equation and then with time independent boundary conditions would look like. So you're going to still have that k second partial of u with respect to x. But you're going to have plus f of x equals partial u, partial t. Your u of 0t is going to be equal to u of 0. So it's not going to be equal to 0. And your u of lt is going to be equal to u of 1. And then that u of x0 will still be equal to f of x. So everything in red is non-homogeneous. So if you have this, it means that you have a non-homogeneous problem. If these two are not 0, non-homogeneous. So what does this represent? This again represents the heat in a rod of length L. This is heat that is being generated internally. So you might want to write this down. This is heat being generated internally at a rate of f of x. And then obviously the ends are being held at temperatures again, this time u0 and u1, not at 0. Okay. So when you have a problem like this, here's the basic solving idea. You are going to change the dependent variable, u, to a new dependent variable, v. And here's what it's going to look like. Normally, you're looking for u of xt. Instead, that's going to be equal to v of xt plus, is that psi?
Yeah.
Okay, good. Psi. So then you're actually going to have two different equations to solve. So then your partial differential equation with your boundary conditions becomes the following. First equation that you're going to have to solve is k times the second derivative of psi plus f of x equals 0. And you have two conditions. Psi of 0 equals u of 0. Psi of L equals U1. Second equation that you will end up solving is going to look very similar to what we've done before. It's going to be k, the second partial of v with respect to x, equals the partial of v with respect to t. And then you're going to have v of 0t equals 0, v of lt equals 0. And then your v of x0 will be f of x, subtract psi of x. Now, when we do an example, I will show you why this is the case. This is not something that you need to memorize. So then in your equation A, you're going to be solving for psi of x. In that problem B, you'll be solving for v of xt. Bless you. So then your solution for u will be the solution for A, add the solution that you get in B. Okay, it's easiest to see this process just by doing an example. Now, here's the bad news with this section. There is no shortcut to these problems. So remember how in heat we solved the general equation and you could use that the majority of the time? That will not be the case here. You're going to have to solve each question individually. There's not going to be any shortcut to get to the end. We will only be doing this one example together. Bless you. So here's your example. K times the second partial of u with respect to x, add r is equal to the partial of u with respect to t. X is between 0 and 1, and t is greater than 0. Your conditions, u of 0t equals 0, u of 1t equals u1, u of x0 equals f of x. Okay, so the initial example I gave you was heat. This one is still heat. Process is the same for wave. So if it's a wave equation, you're still going to carry it out the same way. Okay, so here's how your solution is going to start. We are looking for u of xt, but we said that u of xt is going to be v of xt, add psi of x. So ultimately, we're going to be finding these two, adding them together to get u. Next, what you're going to do is you are going to substitute this into the equation up here. So we're going to need the second partial of u with respect to x, and we're going to need the first partial of u with respect to t. So that's what I'm going to do next, is I'm going to find those two. So the second partial of u with respect to x is going to be the second partial of v with respect to x, and then the second derivative of psi. So then I want the partial of u with respect to t, because I'm going to need that. That'll be the partial of v with respect to t. Psi doesn't have a t in it, so that just goes away. Now we need to substitute into our partial differential equation. So we have k times the second partial with respect to x, so that's here. So we have k times the partial of v with respect to x plus k times second derivative of psi plus r equals partial of u with respect to t, which is really partial of v with respect to t. Rachel.
Where did you get the partial u equals partial v?
I just took the derivative of this with respect to t.
Okay. Why would we do that? I'm sorry, I was writing. That's line after solution.
This,
Yeah.
so that we can substitute back into here.
Okay.
Because this is going to help us now find the two equations that we need to solve. Okay, so this, before where we wrote those equations A and B, this is where A and B are going to come from. This looks similar to something that you've already solved. So that will be your equation B. Your equation B will be K times the partial of V with respect to X equals partial of V with respect to T. In order for those to be equal, this has to equal 0. So that will be your equation A then. So we're going to have to solve both of those. Eventually we'll go back to the conditions and figure out what conditions we're using to find constants. But ultimately these are the two equations we're going to need to solve. A is easier to solve, so I'm going to start with that one. This one you're just going to be able to integrate. So get psi alone. Negative r and k are just constants. I'm going to integrate with respect to x. So I get the first derivative of psi is equal to negative r over kx plus c1. I'm going to integrate again with respect to x. So I get psi of x equals negative r over 2k x squared plus c1x plus c2. Okay, guys with me so far? Okay, so we need to be able to find c1 and c2. So what we're going to do now is we're going to look at the boundary conditions that we were initially given. First boundary condition we were given was u of 0t. Now, based on the definition of u, so based on this u right here, if I'm looking at u of 0t, I'm plugging in a 0 and a 0. So u of 0t is equal to v of 0t plus psi of 0. And that u of 0t was 0. We also know that u of 1t is equal to v of 1t plus psi of 1. And that's equal to u of 1. Okay, if this sum is 0, the easiest case for us is to make psi be 0 and to make v be 0 here. If we want these two summed together to be equal to u1, I'm going to force this to be 0 and this one to be u1. Okay, so then if we look at equation A again, we got our psi of x to be negative r over 2k x squared, add c1x, add c2. We also know that psi of 0 equals 0, and that psi of 1 equals u1. If I plug in 0, 0, I get 0 equals 0 plus c2, telling us c2 equals 0. If I plug in the other condition, I get u1 equals negative r over 2k plus c1. So c1 equals u1 plus r over 2k. So finally, our equation psi is going to be negative r over 2k x squared, add c1 times x using this c1. Okay, questions so far?
How can we just assume that like v of 0 t is equal to 0 and psi of 0 is 0?
We're not assuming that it is, we're forcing it to be,
Okay.
because it'll help us in equation B now.
Okay.
And does that have like implications on what our equation like represents then? Or is it just all the same because in total that still equals the same u equals u1?
So that's just the case that is most convenient to us, but it will still meet all the conditions that we were initially given. Okay, so here's what happens with equation B now. Equation B we already wrote down, so it's k times the second partial of v with respect to x is equal to partial of v with respect to t. So we wrote that down. We also know these two boundary conditions. So we know that v of 0t is equal to 0, and we know that v of 1t is equal to 0. Now, last condition that we haven't used yet, from the original problem, we haven't used this one, the initial condition. So we still need to use the initial condition. U of x0 is going to be equal to v of x0 plus psi of x. How that helps us is it shows us that v of x0 will be equal to u of x0 subtract psi of x. So our v of x0 then is equal to u of x0, so that's f of x, subtract psi of x, so subtracting all of this. So that ends up being plus r over 2k x squared minus r over 2k plus u1 times x. Sorry, I didn't use my space very efficiently. You guys follow me so far? Okay. Does this look familiar? It should, because we've already solved that before, right? This is just a general heat equation. This is generally what we would have called f of x. Okay. I'm not going to go through and solve this again, because we solved it in our notes. So if you want to be reminded on how to separate, go look back at your 12.3 notes. I'm just going to write out what the solution would end up being. Sound good? Okay. So here's what our v of xt then would be. Our v of xt would be 2 over L, the summation from n equals 1 to infinity. In our notes, we used f of x. I don't want to use f of x, though, again, because f of x is here. So I'm going to call all of this g of x instead, just so that we know what f of x we're using. So then this will be the integral from 0 to L of g of x sine of n pi over L x dx e to the negative k n squared pi squared L over L squared t sine of n pi over L x. And then do you remember how we called all of that a of n? So generally what we would write is we would write v of xt is equal to the summation from n equals 1 to infinity of a of n, e to the negative k n squared pi squared t. Remember our L is 1. Sine of n pi x, where a of n is 2 over L, the integral from 0 to L, of f of x plus r over 2k x squared minus r over 2k plus u1 x sine of n pi x dx. Sorry, I ran out of room.
Did you forget the, in the exponent, did you get the over L squared?
L is 1 in our case.
Oh, okay.
Would there be a 2 in front of the summation?
This 2 over L, I brought down here instead.
Oh, okay. Sorry to do that.
I don't know why, that's just the convention. Okay, we follow me so far? Okay. Sometimes this calculation is doable, sometimes it's not. So in this case, not doable because we don't know what f of x is. But a lot of times you will be able to carry out this calculation. You're not just going to be able to leave it as an integral. So we're almost done. Finally, remember that solution, that u of xt, we said that was going to be equal to v of xt, add psi of x. Psi of x is normally put first. So our solution will be negative r over 2k x squared plus r over 2k plus u1 times x. Add the summation from n equals 1 to infinity of a of n e to the negative k n squared pi squared t sine of n pi x, where a of n is what we said above. So this is that psi of x, this is the v of xt. Okay. Questions on the general process?
So with wave, will it just be the same thing except at the start it'll be a double derivative or second derivative?
On both sides. Okay, 2 questions. What happens to this term as t goes to infinity? So what happens to v of xt as t goes to infinity? Goes to 0. So as t goes to infinity, v of xt goes to 0. What is v of xt called then? The what solution? Transient. So this one is called the transient solution. No, this is the steady state solution. Psi is called the steady state solution because as t goes to infinity, u of xt approaches psi of x. So remember how we talked about with heat and wave, you only have to take a few terms before you're going to get a pretty accurate representation of the heat or the wave going on? Okay, well I'm telling you now again, even though we did talk about it and you don't remember. That's why this power is so big that after a few terms it just disappears, or it has very little impact.